Good evening. Am I audible?
Yes, sir.
Matthew, any doubt from last class?
No, sir. No, sir.
Okay. So in last class, we have derived how to calculate combination of spring, that is series combination, parallel combination. So related to this part, I'm asking a question. Suppose you have spring constant of this is K, this is 2K, and this is 3K. Mass of this particular block is M. So find K equivalent and time period for this system. Try to solve using the last concept about series and parallel combination. Matthew, what you can say about this particular arrangement between first two terms? Is
That's
it
parallel.
series? Good. And for this?
That's series.
Just 1 minute. Compare this part, this term and this term. Is it the same thing?
No, because there is a parallel connection in the second one.
First, connect these two terms in parallel. So in parallel, it will be K equivalent equals to K1 plus K2. So K1 is K and K2 is 2K. So on combining these two terms, you will get 3K. Okay.
Okay.
It means The spring on combining these two terms will become like this. So K1 plus K2 will become 3K and this remains 3K. Now, tell me about this combination. Is it series or parallel?
Series.
Just compare the above part with this term and this. This and this are not the same. You may use the other method. Suppose if you displace this particular block towards any one side, let's say I'm displacing towards left. So this spring will get compressed and this spring will get elongated. Is it clear, Matthew?
Yes.
So displacement for both these two springs will be same or different?
It'll be different because one is stretched.
No. Only the notation of compression and extension, but in both spring we have same displacement x. In this part, it is compressing down, and this part it is stretching. Okay, but the displacement in both these two parts is same. So if displacement for a particular combination is same, that will be termed as parallel combination. Okay.
Okay.
So now we can rearrange these two terms. First, K1 is 3K and K2 is also 3K. So K equivalent for this entire part will be 3K plus 3K. So it will be 6K. Mehreen, is it clear? Okay, so time period for any combination will be 2 pi root under m by k equivalent. And this part k equivalent is 6K. So it will be 2 pi root under m by 6K. Matthew, is it clear?
Yes.
Okay, just write it down. Matthew, done?
Yes, sir. Yeah.
Okay. So this is all about combination of spring or simply spring mass system, series combination, parallel combination. Next is simple pendulum. From any rigid support, a string having bob attached to it at any one end start oscillating like this. So if you stretch this particular part to any one side, inclination from this part is theta, length of string is L. So it may experience gravitational force in downward direction, mg. If we extend this particular line, so it will have two different components. One will be along this way and the other will be along this way. So this will be theta. So component of mg along this direction will be mg cos theta, and component of force towards this direction will be mg times sine theta. Matthew, is it clear?
Yes, sir.
I've just resolved the component of mg into two different parts according to its theta. Okay. Now, which of these two forces will responsible to move this bob towards mean position? Mg cos theta or mg sin theta? This is mean position. So which of these two forces is responsible to move this bob towards mean position? Mg cos theta or mg sin theta? Mg cos theta is acting along this way, so it will tend to move this block along this line. And mg sin theta is acting along this way, so it will tend to move this block towards mean position like this. Is it clear? Matthew, is it clear? So mg sin theta will be termed as a restoring force for this particular condition. So you can say restoring force equals to mg times sin theta. Since it is acting opposite of displacement or opposite of direction of motion, so it will be minus of mg sin theta. Now for a small angle, it will be also written as mg times theta. For small theta, sine theta just equals to theta. Now theta equals to length of arc by radius. So let's say displacement of this bob from its mean position is x. So theta will equals to length of arc by its radius, that is L. So it will be minus of mg times x divided by L equals to F restoring force. Matthew, is it clear?
Yes.
Now compare this expression to the above for a spring mass system, where F restoring equals to minus of k times of x. So this particular quantity mg divided by L will behave as spring constant k. So if you compare, restoring force equals to minus of k times of x. So k will equals to mg by L. According to this, time period equals to 2 pi root under m by k. So it will be 2 pi root under m. K we have mg divided by L. So m and m cancel out. So you're left with time period equals to 2 pi root under L by G, the final expression of calculation of simple pendulum, time period of simple pendulum. Matthew, is it clear?
Yes, sir.
Okay, just write it down.
Answer.
Now, related to this last expression, we may write it as this L, it will define effective length of string from axis of rotation to center of mass of bob. This G is called net acceleration related to that system. So you'll be asked, what will happen if you place this particular simple pendulum in a moving left? So let me define you first. If pendulum is placed in moving left, a left may move in three different ways. First, accelerating upward. Second, accelerating downward. And third, free falling. So in this part, downward acceleration will equals to G. Matthew, any doubt?
No, sir, no.
So in first part, when lift is accelerating upward, pseudo force will act towards downward direction. So net acceleration on bob in this case will be G plus A. In second part, since system is accelerating towards downward, so net acceleration due to pseudo force will be G minus A. And in free fall, net acceleration will be G minus G, that will be 0. So if you put these expression to the above part in time period of calculation of simple pendulum, so time period in this part will become 2 pi root under L by G plus A. Since acceleration get increased, so time period of simple pendulum would decrease. In second part, time period equals to under root L by G minus A. Since net acceleration becomes smaller as compared to G, so time period will increases. And third part, time period equals to root under L by net acceleration, which is 0. Any number divided by 0 becomes infinite. It means time period of simple pendulum during this free fall will be infinite. Mehreen, is it clear?
Yes, sir.
Okay, just write it down. So these different conditions you will be asked, and on the basis of which you will have to define time period. Matthew, any doubt? Matthew, done?
Yes, sir.
Okay. Just remember, time period of second pendulum will be 2 seconds. Time period of second pendulum is 2 seconds. In 1 second, it will go on one side, and next 1 second, it will return back to its original position. So total time taken will be 2 seconds. Similarly, you'll be asked, what will happen if you put this particular pendulum on the surface of moon? So on surface of moon, gravity will be lesser as compared to Earth. Is it clear?
Yes, sir.
So if net acceleration decreases on that particular surrounding, so time period of oscillating will increases. Is it clear? Now, this is all about calculation of simple pendulum or time period of simple pendulum and spring mass system. Next is how many different types of oscillation would be. So next is types of oscillation. We mainly have two different types of oscillation. One is called undamped oscillation, and the next one is damped oscillation. So what do you mean by undamped oscillation and damped oscillation? Suppose from any support, a spring attached to a bob is oscillating to and fro. And if there is no any viscous medium and its surrounding, so its amplitude of oscillation will remain same at all instant. So if you have to calculate net force acting on this part, so you will say there is only one force minus of k into y. We may write this particular force as mass times acceleration. So acceleration is minus of k by m times y. We may write it as second differentiation of displacement plus k over m equals to 0. So related to this part, if you simplify it, you'll get y equals to a times sine of omega t. It means oscillation or amplitude of oscillation for this part remains constant. So it will be like this. Y versus t, amplitude remains constant A. So this oscillation is called undamped oscillation. Matthew, is it clear?
Yes, sir.
Now suppose if this system is placed in any viscous medium, a bob attached with this spring mass system is placed in any viscous medium. It means it will be any fluid. So this viscous medium will tend to oppose its motion. So during oscillation, it may experience different force, like net force will be due to its oscillation, damping force minus of B times V, and this spring force minus of K into Y. So acceleration will be B divided by M into velocity minus k by m into displacement. B times V is called viscous force is experienced by this particular object during this particular viscous medium, defined by Stokes' law, F equals to 6 pi eta R times V. So this particular term from this point to this point is called B, damping constant, multiplied by V. And since this force is opposing in nature, so they will have negative sign with it. Matthew, is it clear?
Yes, sir.
So if you simplify this particular part, we may write acceleration as second differentiation of displacement. Move this term to left side. So B divided by M. We may write velocity as dy over dt plus k by m multiplied by y equals to 0. So in this part, we have three different terms. So if you simplify this particular expression, you will get like y equals to some a naught e to the power some constant b divided by 2m into t multiplied by cos omega dash t plus some phase phi. You have to define or keep in mind only this expression, which is defining amplitude. So from this part, we can write a equals to a naught e to the power minus b over 2 times t. It means amplitude is continuously decreasing with respect to time, or it's exponentially decreasing. So if you plot graph related to this part, it will be like this. Displacement versus time, or simply amplitude versus time. So it is going like this. Maximum amplitude a naught, and with change in time, it keep on exponentially decreasing. So at some time, it may get stopped completely. Matthew, is it clear?
Can I explain it one more time, sir?
We have two different types of oscillation. One is called undamped oscillation, in which there is no change in
Yes, sir. Yes, sir. I'm
amplitude.
talking about the graph. I don't understand that.
In damped oscillation, if there is some viscous medium, so due to this viscous medium, it will experience some viscous force, which will tend to decrease its amplitude. And according to this expression, we'll get amplitude gets continuously or exponentially decreasing with respect to time. So at some time, it may get stopped completely and becomes 0. Matthew, is it
Yes,
clear?
sir. Yes, sir. Yeah, okay, now I understood.
So this type of oscillation is called damped oscillation. So just write it down to this part, then undefine these two different terms.
Answer.
Mehreen, any doubt?
No, sir.
Okay. So we may define these different terms as first, undamped oscillation. If amplitude of oscillating body remains same, then it is called undamped oscillation. Or if there is no viscous medium, if there is viscous medium, then its amplitude would remain same. Next is damped oscillation. Due to a viscous medium or damping force, amplitude of oscillating body exponentially decreases. This type of oscillation is called damped oscillation. Matthew, any doubt?
No, sir.
This undamped oscillation is also called free oscillation since there is no any external force acting on this particular part to oscillate it. So this is also called free oscillation. But in this damped part, since amplitude is continuously decreasing, so you must need some external agency to oscillate it at constant amplitude. Those type of oscillation which is driven by any external agency so that its amplitude would remain same is termed as forced oscillation. So next is forced oscillation. In viscous medium, to overcome damping force and to keep amplitude of oscillating body remain constant, we need external agency. This type of oscillation is called forced oscillation. It means suppose you have a spring mass system and there is viscous medium in which it is being placed, which will tend to decrease its amplitude. Now, external agency is joined or attached with this part, let's say a tuning fork driven by any oscillator connected to any oscillator. So due to its vibration, this particular bob will also oscillate with respect to it. So there will be a condition in which frequency of oscillating bob and frequency of vibrating this tuning fork may match with each other. This condition is called resonance frequency or resonance condition. So if frequency of oscillating body equals to frequency of oscillator, then it is called resonance frequency. At this point, amplitude of body or bob becomes maximum. Matthew, any doubt?
No, sir.
So these are some different terms related to this oscillation. You'll be asked, just write it down. Matthew, done?
Yep, sir.
Any doubt related to these different terms?
Not yet, sir.
Okay. Mehreen, is it clear up to this part?
Yes, sir.
Okay, so this is all about this whole chapter, that is simple harmonic motion. Okay, so we have just completed. Next,